Imagine standing at the edge of the world. The wind hits you like a wall of broken glass. The temperature, minus 60 degrees Celsius. The ground beneath your feet, if you can even call it that, is buried under nearly 5 kilometers of solid ice. Ice so ancient, so compressed, it glows a haunting blue. There are no trees here, no birds singing, no insects buzzing, no rivers rushing toward the sea, no voices, no life, just the wind and the silence that follows it. This is Antarctica, the coldest, driest, most windless continent on the face of the earth. A place so hostile to life that the largest animal capable of surviving on its land year-round is a midge, an insect barely the size of your thumbnail. Not a polar bear, not a wolf, not even a rabbit, a midge, that's it. That is the apex of life on this continent today, and yet beneath your feet, buried under all that ancient ice and stone and silence, there are bones. Enormous bones. Bones of creatures with teeth the length of your forearm. Bones of animals that once shook the ground with every step. Fossils of ferns and flowering trees and forests, so thick that sunlight barely reached the forest floor. Evidence of rivers that once carved their way through warm, dark soil, soil that smelled of rain and moss and rotting wood, the way a real jungle smells. What if I told you that this frozen wasteland, this was once a jungle? Not a scrubby grassland, not a mild tundra. A full, lush, teeming, dangerous, alive jungle, complete with dinosaurs, sea monsters, predators with crested heads that looked like something straight out of a fever dream, and forests so vast they rivaled anything on Earth today. What if I told you that roughly 100 million years ago, the very ground you'd be standing on, had you been brave or foolish enough to stand here, would have been carpeted in green? That enormous armored dinosaurs swung bladed tails through the undergrowth. That winged beasts with wingspans wider than a London bus soared above those ancient treetops. That in the waters just offshore, creatures longer than a city bus hunted in the shallows, while ancient sharks the size of great whites stalked the deep. This is not science fiction. This is science fact. And today we are going back. All the way back. Past the age of mammals, past the great extinction, past the rise of the very first flowering plants, to a time when Antarctica was not a frozen grave, but a living, breathing, thriving world, a world of impossible creatures, volcanic fury, perpetual darkness, and jaw-dropping wonders. I am David Attenborough, and this is the story of Antarctica when it was still alive. There is a photograph taken from space, one of the most iconic images ever captured by human hands, where you can see our planet in full, the whole thing. Every ocean, every continent, every swirling cloud system dancing above the surface. And if you have ever looked at that image closely, really closely, you will notice something almost hypnotic about it. The way the continents look like puzzle pieces. The way South America seems to reach eastward, almost yearning toward Africa. The way Australia sits alone in the middle of the ocean like it simply got up one day and decided it had had enough of everyone. And right at the very bottom of that image, Antarctica, a white cap, cold and still, sitting at the bottom of the world like the full stop at the end of a very long sentence. But here is the thing about that image. That image is a lie. Not in the way misinformation is a lie, but in the way a photograph of an old man is a lie, because it only captures one moment in what has been an extraordinarily long and complicated life. The Earth you are looking at in that photograph is roughly 4.5 billion years old. And for the overwhelming majority of that time, it looked absolutely nothing like what you see today. The continents you know, Europe, Asia, the Americas, Africa, Australia, and Antarctica, are not permanent features of the planet. They are passengers. Slow, grinding, restless passengers riding atop massive tectonic plates that are in constant, almost imperceptible motion. And over millions of years, those plates have arranged and rearranged themselves in ways that would make the world utterly unrecognizable to us. To understand Antarctica, Not as it is today, but as it truly was, you need to go back. Not decades, not centuries, not even millennia. You need to go back hundreds of millions of years to a time when the world was arranged in a configuration so dramatically different from today that it would feel quite genuinely like standing on an alien planet. And where do we begin? We begin with a name that sounds like something from ancient mythology. Pangaea. Say it slowly. Pangaea. It comes from the Greek pan, meaning all, and Gaia, meaning earth, all earth. And that is exactly what it was, a single colossal supercontinent that contained virtually all of the world's landmass joined together in one enormous unbroken body. If you had been a bird soaring above Pangaea roughly 300 million years ago, you would have seen something that looked almost nothing like any map you have ever studied. One great mass of land, surrounded by a single vast ocean called the Panthalassa, stretching horizon to horizon in every direction. Now Pangaea did not last. Nothing lasts really when you are dealing with geological time. The forces of plate tectonics, those slow grinding movements of the Earth's crust, had other plans, and so gradually over tens of millions of years, Pangaea began to tear itself apart. It cracked. It drifted. It fractured into two enormous landmasses, Laurasia in the north and a vast southern supercontinent that is crucial to our story today. Gondwana, Gondwana, even the name sounds ancient. And it was a vast southern landmass that contained within its borders the future outlines of South America, Africa, India, Australia, and Antarctica. All of them locked together in a warm, dense, extraordinary embrace. And Antarctica, at this point, was not at the bottom of the world. Not yet. It was situated further north, its latitude more comparable to the southern parts of modern-day Chile and Argentina than the frozen pole it now occupies. Warmer, greener, and very much alive. Now let us talk about the atmosphere, because this is where things get particularly fascinating. We live today in a world where carbon dioxide levels in the atmosphere have become a source of enormous concern, and rightly so. But the irony of our current climate anxiety is that for much of Earth's deep history, carbon dioxide levels were dramatically, almost incomprehensibly higher than they are today. During the Mesozoic era, the great age that encompasses the Triassic, Jurassic, and Cretaceous periods, CO2 concentrations in the atmosphere were many times higher than modern levels. And the result of that was a planet that was, quite simply, much warmer from pole to pole. There were no polar ice caps during large stretches of the Mesozoic. The deep ocean was warmer. The average global temperature was higher. And critically for our story, even the southernmost reaches of the planet, even the landmass that would one day become the frozen wasteland we call Antarctica, were bathed in a climate that was not just survivable, but genuinely hospitable to life. Picture it, you are standing on what will one day be Antarctica. But right now, there is no ice. There is no permanent snow. There is no howling polar wind stripping the warmth from your bones. Instead, beneath your feet is dark, rich soil, the kind of soil that holds moisture and smells of earth and life. Around you, forests stretch in every direction, not the sparse, scrubby vegetation you might associate with cold climates, real forests. Dense, layered, complex forests of ancient conifers towering above your head. Their trunks broad and rough with bark, their canopies blocking out great patches of sky. Beneath them, ferns, enormous, ancient ferns, carpet the forest floor in every shade of green. And alongside these strange and fascinating plants, called Bennettitalians, which look superficially like modern cycads, but are their own extraordinary family, long since lost to extinction, adding texture and variety to the understory. The air is warm, not tropical, but comfortably warm, something like southern Chile on a mild summer's day. Perhaps 17 or 18 degrees Celsius on a typical afternoon, the kind of temperature where you would roll up your sleeves and feel perfectly content. And this warmth is not consistent year-round. There are seasons here, and those seasons are made strange and dramatic by Antarctica's position on the globe, which even then placed it at latitudes that meant prolonged periods of darkness in winter and extended light in summer. But in the warm months, those long days flood the forests with golden light, and everything grows. Water is everywhere. Rivers wind through the landscape, carrying sediment and nutrients from the highlands to lower-lying plains. Lakes sit still and dark between the trees, their surfaces reflecting the sky. Swamps and marshes fill the lower ground, thick with aquatic plants and humming with insect life. Because yes, there are insects here, many of them, beetles scuttling through the leaf litter. And if you are of a particularly robust constitution and an undying hatred of small crawling things, cockroaches too, ancient relatives of the ones that will one day share your kitchen, going about their business with the same magnificent indifference to their surroundings that their descendants will still display 200 million years in the future. This is the Jurassic period, and this is Antarctica, not a frozen grave, a living, breathing, growing world. The forests dominate, but they are not uniform. They shift and change as you move across the landscape. In some areas, the conifers reign supreme, ancient families of trees that will one day give rise to familiar modern species, but are here in forms that would look subtly, uncannily different to modern eyes. In other areas, the ferns take over, creating broad green carpets of vegetation that sway in the breeze like something out of a dream. And along the rivers and lakes, the vegetation becomes denser and more lush, the moisture drawing life inward. Now, you might be wondering, how do we know any of this? Antarctica today is buried under kilometers of ice. How can paleontologists possibly reconstruct a picture this vivid from something so deeply frozen and remote? The answer, as so often in science, is fossils. Extraordinary, painstakingly discovered, mind-bendingly ancient fossils. Fossilized wood, fossilized leaves, fossilized pollen. Fossilized soil horizons, each one a tiny window into a lost world. Scientists have spent decades working in some of the most brutal conditions on Earth, temperatures that freeze exposed skin in minutes, winds that can knock a person flat, to retrieve these fragments of the past. And from those fragments, bit by bit, like assembling the world's most complicated jigsaw puzzle, they have built this picture. One of the most important of these fossil sites, one that has given us an extraordinary glimpse into Jurassic Antarctica, is a formation called Hansen Hill, located on Mount Kirkpatrick in the Transantarctic Mountains. Today, Hansen Hill is surrounded by glaciers. It is a place of ice and wind and absolute desolation. But when scientists analyze the rocks here and date them back to the middle Sinemurian stage of the early Jurassic, roughly 190 to 194 million years ago, a very different world comes into focus. The climate indicators embedded in those ancient rocks suggest that the region was far warmer than it is today. Around 17 to 18 degrees Celsius on average, comparable to the climate of modern southern Chile. The fossilized plant material confirms dense vegetation. And buried among all of it, something even more extraordinary than plants or insects or ancient beetles. Bones. Large bones, strange bones, bones that tell us something remarkable and thrilling about who was living here and what they were doing all those millions of years ago. Because Antarctica, it turns out, was not just a jungle. It was a jungle with dinosaurs, and we are about to meet them. There is something almost philosophical about the discovery of dinosaur fossils in Antarctica. When most people think of dinosaurs, when most people close their eyes and picture those magnificent, terrifying, impossible creatures, they imagine them in jungles, in swamps, in the vast plains of Cretaceous North America or the forests of Jurassic Africa. They do not imagine them in Antarctica, because Antarctica, in the modern imagination, is a place that belongs to cold and emptiness and silence, not to roaring, thundering, living things. And yet here we are. The Hansen Hill Formation has delivered us some of the most astonishing fossils in Antarctic history. And what those fossils tell us is that by the early Jurassic period, Antarctica was already a place teeming with dinosaurs, a diverse, complicated, layered community of creatures that were living, hunting, feeding, and dying in the shadow of those ancient conifer forests. Let us start with the ones you might be less familiar with, because they are, in their own quiet way, just as fascinating as the giants. Among the most numerous dinosaurs found in the Hansen Hill Formation are animals belonging to a group called the sauropodomorphs, and specifically, a primitive branch of that group called the Massospondylids. Now, if you know your dinosaur family trees, you will know that the sauropods, those colossal, long-necked, long-tailed giants that represent some of the largest animals ever to walk the earth, belong to a broader group called Sauropodomorpha, and Massospondylids are some of the earliest, most primitive members of that lineage. But here is the thing about these early sauropodomorphs: they looked absolutely nothing like what you might picture when you think of a sauropod. Forget the enormous neck stretching up into the treetops. Forget the thunderous body the size of a house. Forget the slow, ponderous, ground-shaking movements. These animals were small. Many of them were bipedal, walking on 2 legs rather than 4. And in terms of size, many were no larger than a modern deer. Slender, lightly built, quick on their feet. They were grazers and browsers, moving through the understory of the ancient forests, feeding on the vegetation that grew in dense carpets beneath the taller trees. Among them, in the Hansen Hill Formation, were multiple species of these primitive sauropodomorphs, nimble, curious-looking creatures that represent some of the earliest dinosaurs to set foot on the Antarctic continent. And what makes their presence here so fascinating is this: they were living at exactly the same time as a group of far more advanced dinosaurs, true derived sauropods. Not the giants that would come later, but animals that were already showing the characteristic long neck, large body, and quadrupedal posture of the classic sauropod form. Think about what that means. You have, in the same ecosystem, in the same forests, living side by side, some of the most primitive, earliest members of the sauropod family tree, and some of the more derived, more advanced ones. It is, as some researchers have described it, almost like having ancient hominids suddenly reappear and start living alongside modern humans. A snapshot of evolution caught mid-stride, preserved in the rock of a continent that nobody expected to yield such richness. And then there is the Glacialisaurus, even among the more impressive members of this Antarctic community, Glacialisaurus, which translates, with almost poetic appropriateness, to frozen lizard, stands out. This was one of the larger Massospondylids known from the formation, measuring up to approximately 6 meters, 20 feet in length, and carrying a weight comparable to that of an Asian elephant. In terms of the Jurassic Antarctic landscape, this was a genuinely sizable animal, a large browser moving through the forests on powerful legs, reaching up into the vegetation for food, leaving deep footprints in the soft, damp soil beside the rivers. But the most extraordinary creature discovered at Hansen Hill is not a herbivore at all. It is a predator, and it is extraordinary not just because of its size, its anatomy, or its behavior, though all of those things are remarkable, but because of its head. Allow me to introduce you to the Cryolophosaurus elioti. The name means frozen crested lizard, and that crest, that extraordinary, bizarre, utterly distinctive crest, is the first thing you notice. Sitting on top of the skull of this animal, extending from side to side in an orientation that is almost unique among theropod dinosaurs, is a prominent bony crest, not running front to back, the way many crested dinosaurs carry their ornamentation, but laterally, side to side, like an elaborate pompadour swept across the top of the head. And that is, quite naturally, why paleontologists gave it a nickname that has stuck for decades, Elvisaurus. After the king himself, Elvis Presley, whose legendary pompadour hairstyle is apparently timeless enough to be commemorated in the anatomy of a dinosaur that lived 194 million years ago. There is something genuinely delightful about that. The crest, structurally, is hollow and relatively delicate, certainly not the kind of anatomy designed for combat or structural defense. Based on what we know about similar crests in other dinosaurs, the most widely accepted hypothesis is that it served a display function, a signal of health, maturity, and genetic fitness used to attract mates or establish social hierarchy within the species. Interestingly, both males and females of the species appear to have possessed this crest, which complicates simple mate attraction explanations and suggests that the social dynamics of Cryolophosaurus may have been more nuanced and complex than we might initially assume. But whatever role its crest played in its social life, make no mistake, this animal was not a performer. It was a predator, and a formidable one. First discovered in 1994 by a team from Ohio State University, the Cryolophosaurus was a theropod dinosaur, part of the same broad group that would eventually, much later, give rise to some of the most famous predators in the fossil record, and it was large. Mature specimens reached approximately 7 meters, 23 feet in length, and weighed somewhere between half a ton and 2/3 of a ton. Now let that sink in for a moment. This is an animal the size of a city bus, living in Antarctica, 194 million years ago, but its size alone is not the most remarkable thing about the Cryolophosaurus. What truly elevates this creature into a category of its own is what it represents in the broader context of early Jurassic paleontology, because the Cryolophosaurus holds a record that most people have never heard of. It is the largest known theropod from the entire early Jurassic period, anywhere on Earth. Not just in Antarctica, everywhere. Think about that in the context of Antarctica today. Today, the largest land predator on the Antarctic continent is a midge, an insect, an organism so small that you could hold dozens of them comfortably in the palm of your hand. And yet, once upon a time, the Antarctic continent was home to the single largest land predator anywhere on the planet for its era. The contrast is almost too vast to fully comprehend. The Cryolophosaurus was built for hunting. Powerful arms ending in curved gripping claws, inward curving teeth designed not just to cut, but to hold, engineered to keep struggling prey from escaping once caught, and the evidence suggests it used these tools extensively. Bite marks consistent with Cryolophosaurus teeth have been found on the bones of other animals in the Hansen Hill Formation, telling us exactly what was on the menu. Its primary prey seems to have been other dinosaurs, the sauropodomorphs, the ornithischians, the other residents of the Antarctic forest. But for younger, smaller individuals, the diet appears to have extended to non-dinosaur animals as well, including docodontids and other small early mammals and mammal-like creatures. The Antarctic forest was evidently a place where the food chain was very clearly established, and the Cryolophosaurus sat firmly at the top of it. And then there is the darker side of this story. Because among the specimens of Cryolophosaurus that have been found, paleontologists have identified something unexpected and rather grim signs of cannibalism. Multiple individuals bearing the marks of their own kind, bone material that had been gnawed, scavenged and consumed by fellow Cryolophosauruses. In one particularly striking case, a juvenile, a young, small individual appeared to have been feeding on the carcass of a much larger adult. Now, cannibalism is not unheard of in the animal kingdom. Many predatory species, under conditions of food scarcity or high population stress, will consume members of their own kind. And this discovery at Hansen Hill hints at something important about the nature of Jurassic Antarctica, that beneath the green and the warmth and the apparently hospitable surface, there was genuine pressure on the ecosystem. Resources could become scarce. Competition was fierce, and when things got difficult, even the king of the Antarctic forest was not safe from the hunger of its own offspring. Alongside the Cryolophosaurus, the Hansen Hill Formation also contains evidence of other theropods, smaller, less well-known, but equally real residents of this ancient jungle. Ceratosauroid-like animals, various ornithischians, a cast of characters that, taken together, paint a picture of an ecosystem of real complexity and diversity. And beyond the dinosaurs, the forest itself was alive with smaller life. Beetles moving through the undergrowth, cockroaches navigating the leaf litter, Ancient insects whose descendants will still be recognizable to us millions of years in the future. A whole world of small, persistent, resilient life, filling every niche and crevice of the Antarctic jungle. It was, by any measure, a remarkable place. Warm, green, alive, and ruled at its apex by one of the most impressive predators of its age, a crested, pompadoured, 7-meter killing machine that stalked the ancient forests of a continent that would one day be buried under kilometres of ice. But the story of Jurassic Antarctica is not purely one of life and beauty. Beneath the surface of this green world, forces were at work that would test every creature living here to its absolute limits. And the scars those forces left behind tell us something profound about just how thin the line between flourishing and catastrophe really is. There is a tendency, when we talk about prehistoric worlds, to paint them in broad strokes of wonder and beauty. And there is genuine wonder here. We have seen that. A warm continent, lush forests, rivers and lakes and swamps, dinosaurs moving through the trees. Life, abundant and extraordinary, in a place that today holds almost none of it. But nature has never been a gentle thing. And Jurassic Antarctica, for all its green glory, was a place that could turn brutal without warning. Buried within the Hansen Hill Formation, among the fossils of ancient ferns and the bones of Cryolophosaurus and the remains of primitive sauropodomorphs, paleontologists have found something unexpected and rather ominous: massive buildups of volcanic material, layers of ash and pyroclastic deposits thick enough to tell a very clear story that during the period when these dinosaurs were alive, the region was under the periodic influence of significant volcanic activity, not distant background rumbling, but genuine, devastating local eruptions capable of fundamentally reshaping the landscape. Now, volcanoes are extraordinary things. They are terrifying in the immediate term: pyroclastic flows moving faster than a racing car, walls of superheated gas and ash that incinerate everything in their path, lava flows advancing with slow but unstoppable purpose across the forest floor. If you had been standing in Jurassic Antarctica on the day one of these eruptions took place, the scene would have been apocalyptic. The sky would have turned dark with ash and smoke. The air would have become unbreathable. The heat of the flows would have ignited the ancient forests, sending walls of fire racing through the conifers and ferns, consuming everything they touched. And the evidence suggests this is exactly what happened. Fossilized evidence of wildfires has been found in the formation: charred ancient wood, burned plant material, the unmistakable signature of catastrophic fire having moved through the landscape. These were not small, contained fires. The scale of the evidence suggests that entire sections of the Antarctic forest were periodically devastated, landscapes transformed in a matter of hours from dense green jungle to blackened, smouldering ruin. For the animals living here, the consequences would have been severe. Food sources vanished, water supplies were contaminated with ash and pyroclastic debris, cover and shelter were destroyed, and in the immediate aftermath of an eruption, survival would have become a brutal, urgent, moment-by-moment calculation. This, perhaps, helps explain the signs of cannibalism we discussed earlier. The Cryolophosaurus feeding on its own kind. When the landscape was periodically stripped of its resources, when prey animals were killed or displaced by fire and volcanic activity, the pressure on predators must have been immense. You eat what is available, even if what is available is your own species. But here is where the story becomes genuinely fascinating, because volcanic events, as catastrophic as they are in the short term, are not purely destructive forces. In the long run, they are some of the most powerful engines of ecological renewal on the planet. Volcanic ash, once it settles and weathers over time, breaks down into extraordinarily fertile soil, rich in minerals and nutrients that support explosive new growth. After the fires died down and the ash settled and the rains came, the landscape would have regenerated. New plants colonizing the blackened soil, new growth pushing through the ash, And in many ways, these periodic volcanic events may have played a crucial role in maintaining the richness and diversity of the Antarctic jungle, resetting the landscape, enriching the soil, and creating conditions for new species and new communities to establish themselves. So the very forces that periodically devastated Jurassic Antarctica also fed it, renewed it, kept it dynamic and alive. But there was a larger, slower force at work as well, one that was changing Antarctica not over years or decades, but over tens of millions of years, and that force was plate tectonics, the same geological engine that had originally assembled Pangaea, and was now, inexorably, pulling it apart. Through the Jurassic and beyond, Gondwana continued its slow fragmentation. India began its long journey northward, eventually to collide with Asia and throw up the Himalayas in the most dramatic geological event of the Cenozoic. Africa began to separate from South America, and Antarctica, our Antarctica, was gradually, steadily being drawn southward and isolated. Around 20 million years after the period recorded in the Hansen Hill Formation, Antarctica had fully separated from the main body of Gondwana and was sitting further south than ever before. It had lost some of its continental neighbours, but it was not yet alone. It still maintained connections to Australia, and the two continents shared a close relationship. In fact, the connection between the two was so strong that they exchanged wildlife, with many of the same animal groups being found on both landmasses. The bromance between Antarctica and Australia, as one might call it, was one of the more charming chapters in the continent's history. And then, around 50 million years after Hansen Hill, even Australia departed, drifting northward on its own tectonic plate, taking its unique fauna with it. And Antarctica was left to navigate the rest of its story largely on its own. By the time the later Cretaceous arrived, roughly 85 million years ago, Antarctica was essentially isolated. Not completely cut off from the rest of the world, periodic land bridges still existed, connecting it intermittently to South America and Australia, allowing animals to cross when conditions permitted, but in most senses it was its own world now. Its own isolated, extraordinary, separate theatre of life. And here is what is remarkable. All of this change, all of this geological upheaval, all of this slow drift toward isolation and a more southerly position, none of it had yet broken Antarctica's spirit, so to speak. None of it had yet ended its green chapter, because the climate of the Cretaceous was even warmer than the Jurassic, and Antarctica, despite its increasingly southern position, was still warm enough, still wet enough, still alive enough to support an ecosystem of extraordinary richness. In fact, if the Jurassic was the prologue of Antarctica's green story, the Cretaceous was the main event, the Golden Age, the period when the continent reached the full, glorious, terrifying peak of its biological diversity and complexity. And that story, the story of Antarctica at its absolute peak, is the story of our next chapter. A chapter of armored dinosaurs and feathered hunters and titanosaurs and monsters in the deep. A chapter of long, dark winters that life learned to navigate and warm, flowering summers that life learned to celebrate. The Jurassic built Antarctica's jungle, the volcanic fires tested it, the drifting continents shaped and isolated it, and the Cretaceous crowned it. Let us go there now. There is a moment, if you have ever stood in a truly ancient forest, one of those rare places where the trees are old enough that they seem to have personalities, where the canopy is so thick that the light filters down in slow golden columns, where the air smells of moss and damp earth and something indefinably alive. There is a moment where the noise of the modern world simply falls away, where time somehow feels different, slower, deeper, more honest. Now imagine that feeling, hold it in your mind, and then multiply it by about 85 million years. Because that is where we are going. By the time the late Cretaceous period settled over the southern hemisphere, roughly 85 million years ago, Antarctica had been green for a very long time. Tens of millions of years of forests and rivers and life and fire and renewal. The continent had changed shape. It had drifted south. It had lost its continental neighbors one by one, like guests leaving a party, until only one remains, standing alone with a drink, looking around at the empty room. And yet, despite all of that, despite the growing isolation, despite the increasingly southern latitude, despite the slow creep of longer winters and longer nights, Antarctica was alive, profoundly, extravagantly, astonishingly alive, and not just alive in the modest, quietly persisting way of organisms clinging to the margins of a hostile environment. Alive in the full, roaring, competitive, complex, layered sense of the word. This was an ecosystem firing on all cylinders, a continent at the absolute height of its biological richness. To understand why, we need to understand what the Cretaceous climate was doing, not just in Antarctica, but globally. The Cretaceous period, which ran from roughly 145 million years ago to 66 million years ago, was one of the warmest intervals in the last half-billion years of Earth's history. Carbon dioxide levels in the atmosphere were significantly elevated. Average global temperatures were higher than today. The polar regions, while still experiencing the dramatic seasonal light cycles that their position on the globe dictates, were not yet cold enough to accumulate permanent ice sheets. The deep ocean was warmer, even at the poles. The baseline temperature was dramatically above freezing for much of the year. For Antarctica, this meant something remarkable. Fossilized soil samples from the late Cretaceous layers of the Antarctic rock record suggest that the climate here was broadly comparable to what we would today call a temperate zone. Not tropical, not the steaming equatorial heat of a rainforest, but warm, seasonal, and genuinely hospitable. Mean temperatures in the warmer months could reach highs comparable to modern-day Kenya, around 25 degrees Celsius on a warm summer's day. Think about that for a moment. A summer day in Antarctica 85 million years ago, roughly as warm as a summer afternoon in Nairobi today. The forests had changed enormously since the Jurassic. The ancient conifers and ferns of the earlier period were still present. Some of those ancient lineages are extraordinarily persistent, but they were now joined and in many places supplanted by something new, something that, in the grand sweep of Earth's history, was still a relatively recent arrival, something that would go on to transform the face of every continent on the planet. Flowering plants. The angiosperms, the broad, enormously diverse group of plants that produce flowers and enclosed seeds, had first appeared in the early Cretaceous, and by the time the late Cretaceous arrived, they were doing what flowering plants do so extraordinarily well: spreading, diversifying, colonizing, adapting. In Antarctica's Cretaceous forests, angiosperms were becoming increasingly dominant, their broad leaves catching the long summer light, their flowers drawing in pollinators, their seeds dispersing across the landscape on wind and water. Among the most significant of these new plant colonizers were the ancestors of a group called Nothofagus, the southern beeches. These hardy, beautiful trees, whose modern descendants still grow across the southern hemisphere in places like Patagonia, New Zealand, and southern Australia, were becoming a defining feature of the Antarctic forest landscape. And the environment they helped create, a layered, complex, temperate forest of southern beeches, conifers, ferns, and undergrowth, would have looked in some ways not entirely unlike certain forests you can visit today. If you have ever walked through the ancient Valdivian forests of southern Chile, or the beech forests of New Zealand's South Island, or the cool temperate rainforests of Tasmania, you have glimpsed something of what Cretaceous Antarctica may have felt like: green, rich, layered, alive with the sound and movement of countless organisms. And alongside the Araucarian conifers and the spreading angiosperms, there were ferns, ancient, persistent, magnificently adapted ferns that carpeted the forest floor and filled the spaces between the taller trees. In the wetter, lower areas near rivers and lakes, the vegetation became even denser and more varied. Aquatic plants filled the shallows, reed-like organisms lined the riverbanks. The whole landscape was a mosaic of different habitats: upland forest, riverine woodland, wetland, open clearings created by past volcanic activity or ancient storms, each one occupied by its own particular community of organisms. But here is something important, something that gives this beautiful picture a more complex, more human quality. Because for all the warmth and greenness and apparent abundance of Cretaceous Antarctica, there was one feature of life here that no amount of warmth could fully offset. One aspect of the continent's position on the globe that made it different from every other green place on Earth. The darkness. Antarctica sits at a latitude that, even today, experiences extreme seasonal variation in daylight. In summer, the sun does not set. Day after day of continuous light, the sun tracing low circles around the horizon but never quite dipping below it. And in winter, the opposite. Darkness, long, deep, profound darkness. In modern Antarctica, this means months of the midnight sun in summer and months of polar night in winter. In the Cretaceous, the situation was similar in its fundamental mechanics, if somewhat different in its absolute extremes, given the slightly different position and the warmer overall climate. But the evidence still suggests that Cretaceous Antarctica experienced prolonged periods of winter darkness. Researchers have estimated that the region could have experienced as many as 4 consecutive months of perpetual darkness. 4 months during which the only light would have come from the stars, from the moon, and in a detail that is simultaneously beautiful and menacing from the occasional glow of active volcanoes, illuminating the darkness on the horizon. 4 months of darkness. Think about what that means for an ecosystem. The plants that depend on photosynthesis have to survive it, through stored energy, through deciduous strategies, through underground root systems that can wait out the dark months and explode back into growth when the light returns. The herbivores that depend on those plants have to find food through it, migrating, storing fat, feeding on whatever remains available through the winter months. And the predators that depend on those herbivores have to hunt through it, and they did. Life found a way, as it always does, as it always has. The evidence of animal life in Cretaceous Antarctica is rich and varied. Fossilized bones, teeth, footprints and fragments of shell and scale tell the story of an ecosystem that was, by any measure, extraordinarily diverse. And among all the animals that called this continent home during its golden age, it is the dinosaurs that capture our attention first. Because in the late Cretaceous, Antarctica had dinosaurs of a complexity and variety that dwarfs anything seen here in the Jurassic. Among the most intriguing of the plant-eaters was a stocky armored dinosaur called the Antarctopelta oliveroi, whose very name carries that beautiful combination of the continent and the biology. Antarctic shield. This was an ankylosaur, a member of that wonderfully tank-like group of armored dinosaurs that walked on 4 short, powerful legs and carried an extraordinary natural armor across their backs and sides. The Antarctopelta was a medium-sized member of this group, measuring somewhere between 4 and 6 meters in length, carrying a weight roughly comparable to a large female bison. Like its relatives elsewhere in the world, the Antarctopelta was covered in osteoderms, bony plates embedded in the skin, creating a mosaic of natural armor across its back, flanks and tail. This armor would have provided formidable protection against the teeth and claws of the predators that shared its world. But it is the tail of this animal that truly commands attention. Unlike some of its more famous relatives, the Ankylosaurus of North America, for instance, with its massive, club-like tail designed to deliver bone-crushing blows, the Antarctopelta had a different solution, something arguably more ingenious. As the osteoderms progressed toward the tip of the tail, they began to change in shape, they elongated, they flattened. They arranged themselves into structures that, viewed from above, bore a striking resemblance to a weapon that would not be invented by humans for another 85 million years or so. The maquahuitl, the extraordinary Mesoamerican weapon used by Aztec warriors, a wooden club edged with blades of razor-sharp obsidian. According to accounts left by Spanish conquistadors who encountered it on the battlefield, a maquahuitl in skilled hands was capable of decapitating a horse in a single swing. It was, by any measure, one of the most effective cutting weapons ever devised by a human culture. And the Antarctopelta, without any input from human ingenuity whatsoever, had independently arrived at something functionally very similar. A tail that could sweep wide bladed arcs through the air, not crushing like the classic ankylosaur club, but cutting, slicing. A weapon designed not just to stun, but to genuinely wound anything that came too close to the wrong end of this animal. Which naturally prompts a question. Who exactly was all this armor and weaponry designed for? That question leads us directly into the shadows, into the darker corners of the Cretaceous Antarctic forest, into the story of the predators that ruled this place, and one feathered, large-eyed, darkness-adapted nightmare in particular. Darkness is a strange thing. We fear it instinctively, that visceral animal unease that settles over human beings when the light fails and the shapes around us become ambiguous and uncertain. And that fear, most evolutionary biologists would tell you, is not irrational. It is a memory, a deep, inherited memory from a time when the darkness was genuinely dangerous. When things moved in the night that we could not see, could not predict, and could not outrun, in Cretaceous Antarctica, the darkness lasted for months, and something was moving through it. Meet the Imperobata antarcticus. The name means, with wonderful directness, powerful warrior of Antarctica. And everything about this animal, its anatomy, its adaptations, its very existence in this particular environment, suggests that it earned that name many times over, on first impression. If you caught a glimpse of it in the forest, you might think of the velociraptors you have seen in films. The feathered body, the powerful legs, the alert, intelligent posture of an animal that is always calculating, always assessing, always planning its next move. And in some ways, those associations are not entirely wrong. The Imperobata belongs to a group of dinosaurs that is broadly raptor-like in its general organization. But the classification of this animal is more complicated and more interesting than a simple raptor label would suggest. Its current taxonomic placement puts it within a group called the Unenlargiidae, a family of dinosaurs that has traditionally been considered part of the Dromaeosaurid family that includes the famous Velociraptors, but which is increasingly being viewed by some researchers as a distinct lineage in its own right. One of the most notable members of this broader group is the Austroraptor, one of the largest known dromaeosaur-like dinosaurs ever discovered, capable of reaching 6 meters in length and half a ton in weight. The Imperobata, while somewhat smaller than the Austroraptor, was still a genuinely impressive animal. Based on the fossils recovered, it measured over 3 meters in length, more than 10 feet, and was described by the researchers who studied it as being quite robust for its size, solidly built, powerful, not the lightweight, agile sprinter that some raptor family members were, but something heavier, more muscular, more capable of delivering serious damage. And unlike the classic dromaeosaurids, the Imperobata appears to have lacked the prominent sickle claw on its foot that makes animals like the Velociraptor so immediately recognizable. That large, curved, retractable claw, held off the ground when walking, deployed in hunting, was not present, at least not in the exaggerated form seen in other members of the broader family. But before you feel any sense of relief about that, consider what the Imperobata did have instead. Powerful arms, long, curved, gripping hand claws, legs built for both pursuit and restraint, and a mouth full of long, bladed, recurved teeth, teeth designed not just to puncture but to slice, to tear, to pull flesh from bone with maximum efficiency. This was an apex predator, full stop. But what truly makes the Imperobata extraordinary, what elevates it from merely impressive to genuinely remarkable, is how it was adapted to its specific environment. Because remember, this animal was living in a place that spent 4 months of every year in complete darkness. 4 months during which hunting, feeding, and surviving had to continue regardless of the absence of light. The Imperobata was fully feathered, covered, we believe, in a coat of feathers that would have provided insulation against the cold Antarctic winters. But the feathers were not just about warmth. They were about survival in a world where temperature could become lethal. And then there were the eyes. Fossilized skull material from the Imperobiter suggests it possessed notably large eyes, disproportionately large relative to its skull size, in a manner reminiscent of animals adapted for low light conditions. In the modern animal kingdom we see this pattern repeatedly. Owls, cats, tarsiers, many nocturnal or crepuscular predators have evolved enlarged eyes that maximize the collection of available light, allowing them to hunt effectively in conditions where other animals are essentially blind. The Imperobiter appears to have been doing something very similar. Those large eyes in the months of Antarctic winter darkness would have given it a hunting advantage over prey animals that could not see nearly as well in the dark. Picture it. A cold Antarctic night, sometime around 75 million years ago. The stars are brilliant above the treetops, stars that no human eye will ever see, in a sky that no human being will ever stand beneath. The forest is dark and quiet. An Antarctopelta is moving carefully through the undergrowth, feeding on whatever low-growing vegetation persists through the winter months, its armored sides offering it some comfort in the darkness. And then nothing. No sound, no warning, just those large eyes in the dark, closer than expected. And the Imperobiter moves. That is the reality of Cretaceous Antarctica for its herbivores. The armor of the Antarctopelta, those bony plates and that bladed swinging tail, was not decorative. It was existential. It was the difference between surviving an encounter with the Imperobiter and not. But the Imperobiter was not alone in making life difficult for the plant-eaters of Antarctic Cretaceous. Paleontologists working on Antarctic fossil sites have identified evidence of at least one other carnivorous theropod from this period, an animal that remains unclassified and unnamed, its identity still a mystery, but whose bones hint at something even more alarming than the Imperobiter in certain respects. From the fragmentary remains recovered, this unnamed theropod appears to have stood around 2.4 meters tall, roughly 8 feet at the hip, and based on the characteristics of those bones, researchers believe it was likely a megaraptorid. Now, if megaraptorids are new to you, allow me to briefly paint a picture, because this group of dinosaurs is one of the more extraordinary things to have emerged from southern hemisphere paleontology in recent decades. Megaraptorids were large theropods characterized by one feature above all others, their forelimbs, specifically their hand claws. While most theropod predators relied primarily on their jaws as their principal weapon, megaraptorids appear to have invested enormously in their arms and hands. The hand claws of megaraptorids were enormous, curved, powerful, and designed to do something quite specific and rather horrifying: to grip, to penetrate, to gut. The hunting strategy implied by this anatomy is frankly one of the more unpleasant things I can describe. Using those massive hand claws, a megaraptorid is believed to have driven its hands into the body of its prey, gripping and tearing into the internal organs, causing catastrophic internal injuries. The prey animal, essentially skewered and gutted, would then be held and consumed. One researcher's informal description was that the prey was eaten somewhat like a shish kebab. And while that image is darkly comic, the reality for anything on the receiving end of it would have been anything but. An 8-foot-tall, megaraptorid-type theropod with that hunting strategy, roaming through the Cretaceous Antarctic forests alongside the feathered, darkness-adapted Imperobiter, it begins to paint a picture of a place where the plant-eaters were under serious, constant, multi-directional pressure. And then, in a discovery that still has the paleontological community buzzing with excitement, there is evidence from Cretaceous Antarctic formations of something even larger. Something that belongs to a group whose very name carries weight and wonder. Among the most extraordinary finds from Antarctica's Cretaceous layers is a set of incomplete caudal vertebrae, tailbones, from what appears to be a titanosaur. Specifically, the bones belong to a Lithostrochian titanosaur, a member of a subgroup of titanosaurs that ranged enormously in size, from animals that were merely large to animals that were, quite simply, the biggest creatures ever to stand on land. We do not yet know which specific titanosaur lived in Antarctica. the fossil material is too incomplete to assign a definitive genus. But the implications of its existence here are staggering. Titanosaurs were the giants of the dinosaur world, the kind of animals whose existence seems to almost break the rules of what biology should be able to produce. Animals like the Patagoteton or the Argentinosaurus, creatures that could measure over 30 meters from nose to tail and weigh close to 70 tons. If one of those, or anything remotely approaching that scale, was walking through the Cretaceous Antarctic forest, well, the forest would have noticed. Even the smaller titanosaurs, and some lithostratians were considerably smaller than the true giants, were animals of extraordinary presence. Massive, long-necked, ground-shaking, tree-consuming browsers that would have been essentially immune to predation as adults. Even the Imperobata, for all its lethal adaptations, would have given a fully grown titanosaur a respectful distance. Antarctica's Cretaceous was not just rich, it was epic. A continent at the very peak of its biological expression, armored ankylosaurs, swinging bladed tails, feathered hunters stalking through the winter dark, mysterious megaraptorids gutting prey in the undergrowth, and somewhere in the forests, the earth shaking beneath the footsteps of the largest animals ever to walk. And all of this connected in ways that were becoming increasingly important to the wider world beyond Antarctica's shores. Isolation in biology is one of the most powerful forces in the universe. When a population is cut off, truly cut off, with no way in and no way out, evolution takes it somewhere unique. The Galapagos Islands gave us finches and marine iguanas and giant tortoises found nowhere else on Earth. Madagascar, isolated from mainland Africa for tens of millions of years, produced lemurs and fossors, and a dozen other life forms that exist nowhere else in the world. Australia's long isolation gave us marsupials filling every ecological niche that placental mammals occupy elsewhere. A parallel evolutionary experiment running simultaneously and arriving at, sometimes strikingly different, sometimes eerily similar solutions. Isolation does extraordinary things to life. But here is what makes Cretaceous Antarctica so particularly fascinating from a biogeographical perspective. It was not fully isolated, not yet. Not in the way it would become once the final connections broke and the continent drifted into the cold. During the late Cretaceous, Antarctica maintained something remarkable, a series of intermittent land bridges, periodic connections to both South America and, to a lesser extent, Australia. Corridors of land, sometimes broad and stable, sometimes narrow and ephemeral, that allowed animals to move between continents, and move they did. Antarctica during this period was not just an island of life existing in splendid isolation. It was a crossroads, a waypoint, a place where animals from South America and animals from Australia could meet, where genes flowed between populations, where species that had evolved on one continent could colonize another, and where the evolutionary stories of three separate landmasses became briefly, beautifully entangled. The evidence for this crossroads function is written directly into the fossil record. Certain groups of dinosaurs found in South American fossil sites have close relatives whose remains have been found in Antarctica, suggesting that these animals moved through the land bridge at some point, colonizing the southern continent and establishing new Antarctic populations. Conversely, Antarctic lineages appear to have contributed animals that eventually spread northward into South America. The ankylosaurs, for instance, the broader family to which the bladed-tailed Antarctopelta belonged, showed distribution patterns consistent with movement through the Antarctic region. The ornithopods found in Cretaceous Antarctic formations have close relatives in both South America and Australia, reflecting the continent's position as a biological bridge between two otherwise disconnected landmasses, and the presence of titanosaurs in Antarctica fits perfectly with this picture, since titanosaurs were among the dominant large herbivores of Cretaceous South America, and their appearance in Antarctic rocks is consistent with a population that crossed the southern land bridge. It is a picture that, when you step back and look at it whole, is genuinely moving. 3 continents, South America, Antarctica, Australia, connected by thin threads of land, exchanging life across the southern oceans. Animals making journeys they could not have understood, following food and habitat and the blind compulsion of life to fill available space, inadvertently writing a geological story that scientists would spend centuries decoding now. While the land bridge crossings were undoubtedly significant, let us be clear about one thing: Cretaceous Antarctica was not a mere transit zone. It was not just a corridor through which animals passed on their way to somewhere else. It was a destination in its own right, a place with its own unique ecological character, its own evolutionary pressures, its own community of animals adapted specifically to its particular combination of warmth and darkness and volcanic activity and seasonal extremes, and those specific pressures produced specific adaptations. The large eyes of the Imperobiter tuned to the months of Antarctic darkness. The extraordinary bladed tail of the Antarctopelta evolved in response to the specific predators of this specific place. Even the plant life, the dominance of southern beaches and other cold-tolerant angiosperms, reflects a community adapted to conditions unlike anywhere else on Earth. The volcanic activity that had troubled Jurassic Antarctica had not entirely ceased by the Cretaceous. Evidence of ongoing volcanic episodes persists in the geological record from this period as well. And while the specific formations are less well studied than the Jurassic ones, the broader picture suggests that the dynamic, periodically dangerous volcanic character of the continent was still a factor in the lives of the animals living here, still imposing sudden catastrophic pressure, still periodically stripping resources and forcing adaptation and resilience. And yet, by every measure we have, life in Cretaceous Antarctica was not merely persisting in the face of these pressures, it was thriving. The ecosystem had achieved a richness and complexity that represents, in all probability, the high water mark of biological diversity in the history of this continent. More species, more ecological niches filled, more layers and complexity and interaction than at any other period in Antarctica's long and remarkable story. Ornithopods moving in herds through the forest, cropping vegetation at ground level. Ankylosaurs like the Antarctopelta browsing in the denser undergrowth. Somewhere in the deeper forest, the earth trembling as titanosaurs moved between feeding grounds. Small theropods and early birds, because yes, birds were here too. The avian descendants of earlier theropods, already occupying their own niches in the Antarctic ecosystem, darting through the canopy. And in the darkness of winter, the Imperobata moving with those large light-gathering eyes through a forest that seemed, to lesser-equipped organisms, completely impenetrable. Above it all, the sky, and in the sky, something extraordinary. Something that we will come to in the next chapter when we look at the waters surrounding this continent and the incredible cast of creatures that inhabited them. Because if the land of Cretaceous Antarctica was remarkable, the seas around it were another thing entirely. A world of giants and horrors and creatures so strange that they seem to belong to fantasy rather than natural history. But before we plunge beneath the waves, it is worth pausing for one last moment on land, because there is something profound about standing, in imagination, in this Cretaceous Antarctic forest, about appreciating it for what it truly was, not as a curiosity, not as a footnote in the story of a continent that would eventually freeze, but as a genuine wonder. One of the richest, most complex, most extraordinary ecosystems that has ever existed on this planet. We tend to think of Antarctica's story as a story of loss, the journey from jungle to ice sheet, from abundance to emptiness, from life to near lifelessness, and in one sense, that framing is accurate. What existed here has been lost, buried under kilometres of ice, reduced to fragments of fossil and chemical signal in ancient rock. But in another sense, this is not a story of loss at all. It is a story of the astonishing, almost incomprehensible richness of life on this planet, of the capacity of living things to fill space and exploit opportunity and adapt to pressure and build complexity wherever the basic conditions for existence are met. Antarctica was not always empty. It was once so full of life that the ground shook with it, and the waters around it, those were filled with something else entirely. Something that in some cases makes the land-based giants look almost modest by comparison. There is an old human instinct, ancient, pre-rational, buried so deep in the architecture of our nervous systems that no amount of education or sophistication has ever fully dislodged it, that tells us the water is dangerous, not rivers, not lakes, not the gentle shallows of a familiar shore, the deep water. The water where the bottom is too far down to see, where the light dies within the first 100 meters, where the darkness below is absolute and permanent and filled with things that have never needed eyes, because they have never once in their evolutionary history encountered anything resembling light. That water, the water that goes down, we build boats rather than swim. We stay near the shore when we can. We look over the side of a vessel into dark ocean and feel, most of us, a perfectly rational unease. Because somewhere in our oldest memories, the memories that are not personal but biological, written into us by millions of years of being small and soft and vulnerable, we know that the deep water has always been home to things much larger and much more dangerous than us. In the late Cretaceous period, roughly 75 to 80 million years ago, the waters surrounding Antarctica were perhaps the single most dangerous stretch of ocean on the entire planet. Not because of the cold, it was not cold yet, not in the bone-cracking, ice-forming way it would eventually become. The waters were relatively warm, productive, rich in the nutrients that support complex marine ecosystems, rich, consequently, in prey. And wherever there is abundant prey, there is, in time, an abundance of things that eat prey. What inhabited these waters was a collection of marine predators so diverse, so formidable, and in some cases so enormous that even the most seasoned marine biologist transported back to stand on an Antarctic shore in the Cretaceous would find themselves reaching for words that do not quite exist in the scientific vocabulary. Words borrowed from mythology. Words that belong to the language of sea monsters and ancient nightmares. Because that in many ways is precisely what these animals were. Let us begin with the most dominant group, the creatures that during the late Cretaceous had established themselves as the apex predators of marine ecosystems across the entire world. The animals whose fossils have been found in marine deposits on every single continent, including Antarctica. The animals that, in terms of their ecological dominance, their diversity, their sheer predatory efficiency, represented the ultimate expression of the Mesozoic ocean, the Mosasaurs. If you have seen them depicted in popular media, the enormous crocodilian-bodied marine reptiles erupting from the water with terrifying speed and appetite, then you have some visual sense of what these animals were. But what popular depictions rarely convey is the sheer variety of mosasaurs, because they were not one animal, not one body plan, not one hunting strategy. They were a whole radiation of closely related but meaningfully distinct predators, each adapted to its own particular niche in the marine ecosystem, each with its own tools, its own approach, its own particular way of being terrifying. In the waters around Cretaceous Antarctica, there were at least 5 distinct kinds of mosasaur. 5 different species of enormous marine reptile sharing the same stretch of ocean, each carving out its own ecological space, each representing a different answer to the question of how best to be a large predator in a productive Mesozoic sea. The first, and arguably the most famous by name, was a species of Mosasaurus itself. Not the same species as the famous North American forms, but a distinct Antarctic relative known as Mosasaurus cf. Lemonnieri. This was, by any measure, a genuinely massive animal, stretching to approximately 10 meters in length, or 33 feet, from the tip of its highly pointed snout to the end of its laterally flattened tail, 10 meters, that is longer than a London bus. But it was not merely its size that made this animal remarkable, it was its feeding apparatus. The teeth of this Antarctic Mosasaurus were notably smooth and slender, a different shape from the more robust conical teeth seen in other mosasaur species, and combined with what appears to have been an unusually flexible lower jaw. This has led researchers to propose a particularly unpleasant feeding strategy, something called ratchet feeding. The mechanics of ratchet feeding work like this. The animal bites its prey, secures it, holds it, and then, rather than simply swallowing it whole in one gulp or tearing pieces from it, the lower jaw works in a slow, progressive motion like a conveyor belt, like a ratchet mechanism advancing one notch at a time, walking the prey item, bit by bit, down the length of the throat. Slowly, inexorably, with no possibility of escape once the teeth have closed. It is one of those natural history details that you encounter and then cannot quite shake loose from your imagination, the slow mechanical inevitability of it. The prey, still alive, being walked into the gullet of a 10-meter marine reptile, one ratchet at a time. Chemical analysis of the isotopic signatures in Mosasaurus lemonieri fossils suggests it preferred to hunt in deeper water, diving down into the darker layers of the water column where larger, denser prey concentrations could be found, and sharing those deeper waters with it was another mosasaur, a species that, in certain respects, was even more dramatically adapted to life in the depths. The plioplate carpus, a medium-sized relative of Mosasaurus, reaching approximately 6 meters or 18 feet from snout to tail, was in some ways the most specialized deep diver of the Antarctic Mosasaur community, where the Mosasaurus had a long pointed snout adapted for active pursuit hunting. The plioplate carpus had evolved in a very different direction. Its snout was short and stubby. Its eyes, by contrast, were enormous, disproportionately large, designed to maximize light collection in the darkness of the deep ocean, where sunlight barely penetrates and the only illumination is the faint, diffuse blue-gray glow of bioluminescent organisms. With those massive eyes in the deep, dark water, the plioplate carpus used slender, recurved teeth to hunt soft-bodied creatures, cephalopods, squid-like organisms, ammonites, the kinds of prey that inhabit the darker layers of the ocean in vast, swirling concentrations. It was a specialist, an animal exquisitely adapted to its particular niche, living and hunting in a world of darkness that most of its contemporaries never entered. But here is the detail that truly makes the plioplate carpus alarming, and not just as a theoretical prehistoric monster, but as a genuine practical hazard for any organism moving through Cretaceous. Antarctica. Historical fossil specimens of this creature have been recovered from what were in the Cretaceous freshwater riverbeds inland, in rivers. That means the plioplate carpus, this 6-meter, enormous-eyed marine reptile, was capable of entering freshwater environments, of moving inland, of being present, potentially in the very rivers and wetlands that ran through the Antarctic forest interior. Think about that for a moment in practical terms. You are an Antarctopelta, or a young titanosaur, or any of the various ornithopods and smaller dinosaurs that populated the Cretaceous Antarctic forest. You are thirsty. You approach a river. The water is dark, tannin-stained the way rivers in forested areas often are. The color of strong tea, visibility essentially zero beneath the surface. You lower your head to drink. And somewhere beneath that dark water, something with eyes designed for the darkness is already aware of you. Has been aware of you, in fact, since you first began moving through the undergrowth toward the river bank. Because the plioplate carpus, like modern crocodilians, may have been capable of detecting the vibrations and movement of large animals approaching the water's edge. In Cretaceous Antarctica, it is possible that you were never entirely safe from a mosasaur, not even on land. Then there was the Tanniwosaurus, a larger mosasaur, reaching approximately 8 meters or 26 feet in length, whose most distinctive anatomical feature was its snout, which functioned, essentially, as a biological ram, broader and more robust than the pointed snout of the Mosasaurus. The Tanniwosaurus snout was built for impact, suggesting a hunting style that was more aggressive and direct. A generalist predator in the truest sense, the Tanyosaurus appears to have been capable of tackling a wide variety of prey, using its size, its speed, and that reinforced snout to overwhelm animals that other mosasaurs might have avoided. And beyond the three named species, there were others. At least one additional mosasaur whose remains have been found in Antarctic waters, but which has not yet been fully described or named. The diversity of mosasaurs in this single stretch of Cretaceous ocean was, by any measure, extraordinary. But the mosasaurs, for all their dominance, were sharing these waters, and the creatures they were sharing them with were, in their own ways, equally extraordinary. Because the Cretaceous ocean around Antarctica was also home to the last flourishing of one of the most elegant, most distinctive, and most persistently misunderstood groups of marine reptiles in the entire fossil record, the plesiosaurs, long-necked, flipper-propelled, ancient beyond imagining. Plesiosaurs had been swimming in the world's oceans since the Triassic period. And by the late Cretaceous, while they were past their evolutionary peak in terms of global diversity, they were still thriving around Antarctica, represented by multiple distinct families: Aristonectines, Elasmosaurids, and the polycotylids, each with its own body plan, its own hunting strategy, its own ecological relationship to the rich Antarctic waters. The most visually striking were the long-necked forms, Elasmosaurids in particular, whose necks were so extraordinarily elongated that they made up more than half the animal's total body length. An elasmosaurid moving through the water was a sight of impossible elegance, the neck undulating gently, the four powerful flippers driving the body forward, the small head at the tip of that improbable neck scanning the water for prey. That neck was a hunting tool of considerable subtlety. Moving slowly, almost silently through a school of fish, an elasmosaurid could maneuver its head into position among the prey animals without the bulk of its body triggering their escape response. And then, with a speed that belied the slow approach, that small tooth-lined head would snap sideways, snatching fish after fish before the school had time to scatter. A true sushi terror, as one might say, a specialized fish eater of extraordinary elegance and efficiency. But even the plesiosaurs, those ancient, graceful hunters of the Antarctic seas, faced pressure from below, because the waters of Cretaceous Antarctica were not just filled with large reptiles. They were filled with fish, and some of those fish were not content to simply be prey. Some of those fish bit back. Fish have been on this planet for a very long time, longer than the dinosaurs, longer than the first land animals, longer, in fact, than the first forests. The vertebrate story begins in the water, in the ancient seas of the Ordovician and Silurian periods, where the first jawless fish were already experimenting with the basic blueprints of what would eventually become every backboned animal on Earth. And sharks, those ancient cartilaginous, magnificently adapted predators, have been here for almost as long. The oldest definitive shark fossils push back beyond 450 million years. They predate the dinosaurs by nearly 250 million years. They survived every mass extinction event that periodically devastated life on this planet. They were here before the continents separated. They were here before the first tree grew. And they were very much here, in force, in the Cretaceous waters surrounding Antarctica. But to call the creatures we are about to discuss simply sharks would be to dramatically undersell them. Because the sharks of Cretaceous Antarctica were not the familiar great whites and tiger sharks and bull sharks of the modern ocean. They were something older, something stranger, something that in several cases was the direct ancestral lineage of animals that would go on to become legendary. The most significant of them all, in terms of both its ecological dominance and its extraordinary evolutionary legacy, was the Cretalamna. The name may not ring immediate bells. But what if I told you that the Cretalamna is believed by many researchers to be an ancestral relative, a forerunner of the most famous, most feared, most mythologized predatory fish that has ever swum in Earth's oceans? What if I told you that in the teeth of the Cretalamna you can already see, in embryonic form, the design that would eventually be perfected in the jaws of the Megalodon? The Cretalamna was not the Megalodon. Not yet. The Megalodon was a creature of the Miocene and Pliocene, tens of millions of years in the future from the Cretaceous. And where the Megalodon could reach lengths of 15 to 18 meters and weights of 50 tons or more, the Cretaceous Cretalamna specimens found in Antarctic waters were considerably more modest, capping out at around 5 meters in length, or 16 feet, larger than any modern bull shark, comparable in size to a large tiger shark. But nothing like the colossal animal its descendants would eventually become. And yet, even at 5 meters, the Cretalamna was an apex-level threat. Its teeth, rows of them, the classic shark conveyor belt of continuous replacement, were razor-edged, triangular, and designed with what can only be described as elegant ruthlessness. General enough in shape to be versatile, sharp enough to slice through almost anything. And the evidence left in the fossil record is unambiguous about what the Cretalamna was willing to eat. Bite marks consistent with Cretalamna teeth have been found on bony fish, on turtles, on squid and cephalopods, on other sharks, and most remarkably on elasmosaurids and mosasaurs. Marine reptiles that themselves reached lengths of 6, 8, 10 meters. The Cretalamna was attacking animals larger than itself. The largest confirmed prey items bearing evidence of Cretalamna predation were over 9 meters long, 30 feet. The shark, it seems, had always been a confident creature. Sharing these waters at the bottom of the figurative shark hierarchy were several more familiar faces. Angel sharks cruised along the seafloor, lying in ambush beneath a light covering of sediment, erupting upward with terrifying speed to engulf passing bony fish. Dogfish sharks, smaller, more modestly sized, but numerous, occupied the mid-water zones, and in the deeper, darker waters, an ancient species of cow shark called the Notodonodon patrolled. Roughly twice the length of an average adult human, the Notodonodon was a generalist hunter that preferred the deeper, darker layers of the water column, a Cretaceous shadow moving through the Antarctic depths. Then there were the ones that preferred the deepest darkness of all. The ones that, even by the standards of a Cretaceous Antarctic ocean packed with extraordinary life, managed to be genuinely, distinctively strange. The frilled shark. If you have never encountered a frilled shark, either in a nature documentary or, in extremely rare cases, in real life, since they do still exist today, prepare yourself. This is an animal that looks less like a fish and more like something a particularly creative nightmare constructed from spare parts, an eel-like body, elongated and sinuous. A mouth filled with what appears to be a nearly endless arrangement of trident-shaped teeth, approximately 300 of them in total, each one recurved and needle-sharp, arranged in rows that give the impression of a mouth that can grip anything, and eyes that are pale and unsettling in a way that is difficult to fully articulate but impossible to forget. The frilled shark is one of Earth's oldest still-living genera. It has been here, essentially unchanged in its fundamental design, since before the Cretaceous. It is what biologists call a living fossil, an organism whose lineage has persisted with minimal modification for an extraordinary length of time. And during the Cretaceous, the warmer global ocean temperatures allowed it to extend its range much further south than it can today, reaching the waters around Antarctica and doing there what it does, everywhere it goes, hunting in the deep dark water, using those 300 recurved teeth to grip slippery cephalopods and small fish and hold them with absolute certainty while it consumes them. There is something almost philosophical about the frilled shark. Something that puts geological time in perspective. This animal was already ancient when the dinosaurs were alive, and it is still alive today, in the deep water, doing exactly what it has always done. Some things, it turns out, do not need to change. Then there was the goblin shark, another deep water specialist, another inhabitant of the abyss, another face that, in the modern ocean, is so bizarre and unsettling that it seems to belong more to mythology than to biology, that extraordinary extendable jaw shooting forward to engulf prey, those pale, translucent, almost luminous skin tones, that long, flattened rostrum packed with electroreceptors for detecting the faint electrical fields given off by nearby animals. In the modern ocean, goblin sharks are deep-water specialists, sluggish, slow-moving creatures that rely on ambush and their bizarre jaw mechanism rather than speed or power. They are not, despite their appearance, particularly dangerous to large animals. But in Cretaceous Antarctica, there was a goblin shark that broke almost every rule that modern goblin sharks follow. The Scapanorhynchus, first appearing in the Aptian stage of the early Cretaceous, this was a goblin shark unlike any that exists today. The first remarkable thing about it was where it lived, not in the abyss, not in the crushing darkness of the deep ocean, but in relatively shallow coastal environments. It had traded the deep-sea lifestyle of its relatives for something far more aggressive and far more connected to the productive life-rich shallow waters near the shore, and it had the body to match. Where modern goblin sharks are slow and somewhat ungainly, adapted for the deep water, where speed is less important than patience, the Scapanorhynchus possessed an extremely long and powerful tail, plus highly developed flippers that gave it genuine speed and maneuverability. The sluggishness of its modern relatives was entirely absent. It was also without question the largest goblin shark that has ever existed. Specimens suggest it could reach 6.7 meters, 22 feet in length, and likely weighed over a ton. An isometric analysis of its teeth revealed a diet focused primarily on large fish, but the morphology of those teeth designed both to capture slippery prey and to tear enormous chunks of flesh from larger animals made it capable of far more than simple fish catching. And, in a detail that should give anyone pause, remains of Scapanorhynchus have been found not just in marine environments, but in multiple freshwater locations. Like the plioplate Carpus mosasaur, this animal was capable of entering freshwater systems. The rivers of Cretaceous Antarctica were not safe from it. And then there were the fish that were not sharks at all, but were extraordinary in their own rights. The chimeras, sometimes called ghost sharks, though they are not true sharks but close relatives, were, in the Cretaceous, experiencing something of a golden age. Today chimeras are rare, relatively small, and mildly peculiar looking. In the Cretaceous, they were diverse, numerous, and in at least one case, genuinely alarming. The Edaphodon was the largest chimera ever discovered, a giant rabbit-fish-like creature reaching 3.43 meters, over 11 feet in length. But its size, while notable, was not its most dangerous feature. That distinction belonged to its teeth, or rather its tooth plates. Where most fish have individual teeth, the Edaphodon had large, durable dental plates, edged and structured in a way that allowed it to do two very different things simultaneously: crush hard-shelled prey like mollusks and crustaceans, and cut apart larger, softer organisms like fish and marine reptiles. A multi-purpose feeding apparatus of considerable effectiveness. And above all of this, above the mosasaurs and plesiosaurs and sharks and ghost fish filling the Antarctic waters, something flew, something that looked from below like the shadow of a dream, or a nightmare, depending on your perspective. Back in 2019, paleontologists working on James Ross Island in Antarctica made a discovery that completed what might be called the Mesozoic trifecta of Antarctic life: dinosaurs, marine reptiles, and now the third great group of Mesozoic megafauna, a metacarpal bone, a wing bone, was recovered from the rock. And from its dimensions, the implications were immediate and extraordinary. The animal this bone came from was a pterosaur, and it was enormous. Based on the proportions of the recovered bone, researchers estimated a wingspan of over 5 meters, 16 feet across. Longer than the tallest African elephant is tall, the largest known animal ever to have flown over Antarctica. We do not yet know exactly what species this pterosaur was. The fossil material is too fragmentary for a definitive classification. But based on the trends seen in pterosaurs of comparable size and time period, there is a reasonable chance it belonged to or was closely related to the Ashdarchids, the group of pterosaurs that produced some of the largest flying animals in Earth's history. Animals like the Quetzalcoatlus, whose wingspan reached 10 or 11 meters, and which on the ground stood as tall as a modern giraffe. If the Antarctic pterosaur was indeed an Ashdarchid, or a close relative, then its hunting behavior was likely very different from the fish-plucking pterosaurs more commonly depicted in popular media. Ashdarchids are believed to have been largely terrestrial hunters, walking through open landscapes on those enormous folded wings, their long necks reaching down to snatch small animals, young, dinosaurs, lizards and mammals from the ground. The closest living analogy, imperfect as all analogies are, might be a giant ground-stalking stork, which means that in Cretaceous Antarctica, even the sky was not entirely safe. Something with a 5-meter wingspan was looking down from above as well, a shadow passing over the forest canopy. The largest thing that had ever flown over this continent, scanning the ground below with ancient, calculating eyes, land, sea and sky. Every dimension of the Antarctic world was occupied. Every niche filled, every level of the ecosystem stacked with life in extraordinary complexity and variety. This was Antarctica at its absolute peak, its golden age, the fullest, richest, most extraordinary expression of everything this continent was capable of producing. And then, in geological terms, almost without warning, it ended. There is a layer in the rock record, a thin, distinct, globally distributed layer of sediment found on every continent and in the deep ocean floor that marks one of the most significant moments in the history of life on this planet. Geologists and paleontologists call it the KPG boundary, the Cretaceous-Paleogene boundary, the line in the rock that separates the world of the dinosaurs from the world that came after. Above it, mammals, birds, the familiar world, the world that eventually produced us. Below it, everything we have been discussing, the mosasaurs and plesiosaurs, the titanosaurs and ankylosaurs, the feathered hunters and the ancient sharks. The green Antarctic forests and the rivers and the lakes and the volcanic highlands. Everything. That layer of rock, enriched with iridium, a metal rare in Earth's crust but abundant in asteroids, was laid down approximately 66 million years ago. And what deposited it was an event so catastrophic, so globally transformative, that it fundamentally and permanently altered the trajectory of life on Earth. An asteroid, roughly 10 to 15 kilometers in diameter, moving at approximately 20 kilometers per second, arriving with complete indifference to the extraordinary world it was about to destroy, in what is today the Yucatan Peninsula of Mexico, a place called Chicxulub. Now, you might think, as scientists once thought, and as common sense might initially suggest, that Antarctica, sitting at the very bottom of the world, as far as geographically possible from the impact site in present-day Mexico, might have been at least partially spared from the worst of what followed, that its extreme southern position might have offered it some protection, some buffer, that it might perhaps have served as a refuge, a place where some of the Cretaceous megafauna survived, while everything closer to the impact zone was obliterated. This hypothesis was tested directly. Researchers analyzed over 6,000 marine fossils from Antarctic sites, ranging in age from approximately 70 million years ago to 1 million years after the extinction event, a window that captured the world immediately before and immediately after the asteroid impact. These fossils represented a remarkable cross-section of Antarctic marine life: small mollusks, medium-sized fish, giant mosasaurs, everything in between. A comprehensive snapshot of the ecosystem at its peak and then at the moment of its destruction. What they found was unambiguous and brutal. At precisely the horizon corresponding to the asteroid impact, the moment in the fossil record when the KPG boundary layer appears, there was a massive, sudden, catastrophic collapse in the number of species present. Approximately 70% of all species disappeared, not gradually, not over thousands of years of slow decline, but essentially immediately in geological terms. One moment, the full richness of the Antarctic marine ecosystem, the next, 70% of it gone, the same extinction rate as everywhere else on Earth. No refuge, no buffer, no mercy from geography. The asteroid did not care how far Antarctica was from Mexico. And if you had been there on that day in Cretaceous Antarctica 66 million years ago, what would you have experienced? It would have begun with the ground. A magnitude 4 earthquake, not the most extreme seismic event imaginable, but enough to be felt, enough to send ripples across the Antarctic lakes and rivers, enough to startle every animal in the forest into alarm. The earthquake would have arrived within minutes of the impact, the seismic waves traveling through the Earth's crust at several kilometers per second. Then the sky would have begun to change. The ejecta cloud, the vast plume of superheated rock and vapor blasted into the upper atmosphere by the force of the impact, would have begun to spread across the planet. Traveling through the upper atmosphere at extraordinary speed, this cloud of debris would have reached Antarctica within hours from the ground. Looking up, the sky would have darkened. First a thinning of the light, then a brownish ochre dimming, then something like a vast dust storm overhead, stretching from horizon to horizon, blocking the sun. But before the darkness came something worse. As the ejecta particles rained back down through the atmosphere, they heated the air through friction. The upper atmosphere across much of the planet became briefly superheated, hot enough that anything caught in the open without the protection of deep water or underground shelter would have experienced conditions comparable to being inside a heated oven. The thermal pulse was brief, minutes, perhaps an hour at most in any given location, but it was enough. Enough to ignite exposed vegetation, to kill animals caught in the open. In Antarctica, being further from the impact site, the thermal pulse may have been somewhat less intense than at closer locations, but it was not absent. And the fires it ignited in the ancient Antarctic forests, adding to the already substantial burning happening at locations much closer to the impact, would have sent vast columns of black smoke into an already darkening sky, and the ocean was not spared either. The impact had triggered tsunamis, not just in the Gulf of Mexico where the asteroid struck, but propagating outward across every ocean on the planet. By the time those waves reached Antarctic waters, they had traveled tens of thousands of kilometers. But even after that immense journey, the wave height reaching the Antarctic coast has been estimated at approximately 10 meters, 33 feet. The same scale as the devastating tsunami that struck Japan in 2011, an event whose images of walls of water consuming entire coastal towns are still a decade later almost impossible to look at directly. In Cretaceous Antarctica, the shallow coastal areas where the plesiosaurs hunted, where the Mosasaurus patrolled, where the Scaponarhynchus goblin shark roamed the shallows would have been hit by those waves, coastal habitats destroyed, ecosystems that had taken millions of years to build, swept away in minutes. And then came the dark, the long, terrible dark. The dust and soot and sulfur aerosols injected into the upper atmosphere by the impact were enough to significantly block incoming solar radiation across the entire planet. Photosynthesis, the foundation of virtually every food chain on Earth, collapsed. Plants died. Not all at once, but steadily, progressively, as the darkness persisted for months. In a place like Antarctica, which already experienced prolonged winter darkness, the additional blocking of sunlight during what should have been the productive summer months was particularly devastating. The plants that had relied on those long Antarctic summer days to build up the energy reserves that saw them through the winter now had no summer, only more darkness. Without the plants, the herbivores starved. Without the herbivores, the predators starved. Without producers at the base of the marine food chain, the phytoplankton that formed the foundation of the entire ocean ecosystem, the marine food web collapsed from the bottom up. The Antarctopelta, with its magnificent bladed tail and its armored flanks, an animal that had survived volcanic eruptions and long dark winters and the hunting pressure of feathered nightmares in the dark, could not survive the collapse of the plants it depended on. The Imperibata, that magnificent, large-eyed, darkness-adapted hunter, found no prey in the endless winter that followed the impact. The Titanosaurs, those colossal browsers whose feet had shaken the Antarctic ground, they fell silent. The Mosasaurs in the water, the Plesiosaurs, the ancient sharks, the 70% extinction rate in Antarctica's marine fossil record is not an abstraction, it is a body count. Species by species, family by family, the richness of the Antarctic Cretaceous Ocean was dismantled. And yet, and this is important and worth remembering, because it speaks to something fundamental about the resilience of life, not everything died. Some things held on. Some things, through a combination of ecological flexibility, fortunate circumstances, and sheer biological tenacity, survived the worst event in 66 million years and kept going. The Edaphodon, that enormous chimeras with its crushing and cutting tooth plates, survived the extinction event. Its lineage persisted into the Paleogene and beyond. The Cretalamna, the ancestral relative of the Megalodon, also survived. And in doing so, it set in motion the evolutionary trajectory that would eventually, millions of years in the future, produce the largest predatory fish the ocean has ever known. Consider that. The Megalodon, the animal that fills our deepest ocean nightmares. The 60-ton, 18-meter, everything-eating colossus of the Miocene Ocean traces its lineage back to a shark that swam in the Cretaceous waters of Antarctica. The worst mass extinction in 66 million years was, in a roundabout way, a step on the path toward the most impressive marine predator of the Cenozoic. Life, as has been observed before with considerable understatement, finds a way. And Antarctica itself, this continent that had been green for hundreds of millions of years, that had hosted the first Antarctic dinosaurs in the Jurassic, that had reached its golden age in the Cretaceous, that had been home to everything from titanosaurs to feathered hunters, to giant goblin sharks to 5-meter flying reptiles. Antarctica was not finished. Not yet. Not for a long time. After the extinction event, the continent would recover. Slowly, painfully, over millions of years, new ecosystems would rebuild themselves from the survivors. The early Paleogene would see Antarctica still green, still forested, still warm enough for large land animals, still alive in ways that would, many millions of years later, produce wonders of their own. It would take until roughly 34 million years ago, the Eocene-Oligocene boundary, for the final decisive shift to occur. The opening of the Drake Passage between Antarctica and South America, allowing the Antarctic circumpolar current to establish itself and thermally isolate the continent, driving the formation of the permanent ice sheet that covers it today. But that is another story. What we have told today is the story of Antarctica in its prime. In its green, extraordinary, teeming, volcanic, sun-drenched, and dark-wintered prime. The story of a continent that was, for hundreds of millions of years, one of the most remarkable places on the surface of this planet. The ice came eventually, as it always does, in geological time. Things change, continents drift, climates shift, the world rearranges itself indifferent to the extraordinary things it buries in the process, but the bones remain. Deep in the rock, under the ice, waiting for the patient hands of scientists willing to work in brutal cold for the chance to hold a fragment of a world that most people have never imagined existed. They remain, and through them, so does Antarctica's green past, alive in its own way, waiting to be told. So here we are, back on the ice, back in the white, howling, bone-cracking cold of the continent we know today. The wind is back, the silence is back. That vast, featureless expanse of frozen nothing stretching in every direction back. But I wonder, and I hope you wonder too now, whether it looks quite the same to you as it did at the beginning of this journey. Whether the ice feels different when you know what it is covering. Whether the silence sounds different when you know what it has replaced. Because beneath your feet, right now, under kilometers of ancient compressed ice and rock and time, there is a world. A buried world. A world of dark conifer forests, humming with Jurassic insects, of rivers catching the light of a sun that set for the last time on that landscape, roughly 34 million years ago. A world where the ground once shook under the weight of titanosaurs, and the sky was crossed by the shadow of a pterosaur, with a wingspan wider than a city bus. A world where something with a pompadour-shaped crest and the appetite of a 7-meter killing machine was the largest land predator anywhere on Earth, and wore that title, it has to be said, with extraordinary style. It is all still there, frozen, compressed, preserved in the dark. And I think that is one of the most profound things about Antarctica. Not the cold, not the ice, not even the extraordinary scientific value of the continent as a record of Earth's climate history. Though all of those things are genuinely remarkable, the most profound thing about Antarctica is the gap between what it appears to be and what it actually is. The gap between the story its surface tells, empty, barren, lifeless, and the story its depths tell, if you know how to read them. A gap measured not in kilometers, but in time, in hundreds of millions of years of life, and change, and catastrophe, and renewal. We humans are a young species, embarrassingly young by geological standards. Our entire recorded history, every civilization, every empire, every monument, every piece of music and literature and art ever produced, fits into the last 10,000 years or so. The Jurassic dinosaurs of Antarctica lived and died and fossilized roughly 19,000 times longer ago than that. The numbers are so vast that they stop meaning anything to the ordinary, day-to-day coffee and commute part of our minds. We cannot truly feel geological time the way we feel our own lives. We can only gesture at it, approach it with metaphors, try to build mental structures large enough to hold even a fraction of it. And yet, somehow, knowing it matters. Knowing that this frozen continent was once a jungle matters. Knowing that the Cryolophosaurus stalked those ancient forests, that the Imperobator hunted through 4 months of perpetual darkness with those extraordinary eyes, that Mosasaurs ratchet-fed their prey in shallow coastal waters and then swam inland up the rivers. Knowing all of this does something to the imagination, opens something. Makes the world feel bigger and deeper and stranger and richer than it did before. That, I think, is what natural history is really for. Not just the accumulation of facts, not just the cataloguing of species and dates and geological formations, though all of that meticulous, painstaking scientific work is the foundation on which everything else rests. It is for this, for the moment when the facts arrange themselves into a picture vivid enough that you can almost feel the warmth of that Jurassic sun, almost hear the distant rumble of a Cretaceous volcano, almost sense the shadow of a 5-meter pterosaur passing overhead. The Earth has been doing extraordinary things for an extraordinarily long time, long before we were here to watch. Long before there were eyes capable of appreciating it or minds capable of being astonished by it, and the rock remembers, the fossils remember. The iridium-rich layer at the KPG boundary remembers the day the asteroid came and broke the Cretaceous world into before and after. We are the first species in the history of this planet with the capacity to read those memories, to decode them, to hold a fragment of ancient bone in our hands and reconstruct piece by careful piece the animal it came from, the world it lived in, the ecosystem it was part of. That is an extraordinary privilege, and it comes, I think, with a quiet responsibility to pay attention, to remain curious, to never look at a landscape, however barren, however empty, however apparently lifeless, and assume that emptiness is the whole story. Antarctica is not empty, it is full, full of time, full of memory, full of the ghosts of a world more strange and rich and wonderful than almost anything we could invent, and it is still giving up its secrets. With every new field season, every new expedition into those brutal conditions, every new fossil carefully extracted from rock that has held it for tens or hundreds of millions of years, the picture grows a little clearer, a little more vivid. A new species here, a new formation there, a bone that changes what we thought we knew, or confirms something we suspected, or opens an entirely new question that nobody had thought to ask before. That is the nature of science. That is its beauty. It is never finished. There is always more. So the next time you see a photograph of Antarctica, that white cap at the bottom of the world, cold and still and apparently empty, I hope you see something else too. I hope you see, just beneath the ice, the shadow of a forest, the ghost of a river, the distant echoing impression of a world that was, for a very long time, magnificently alive. It was here. It happened, and now you know. If this journey through deep time has left you as astonished as it leaves me, if the thought of Antarctica as a jungle, as a world of Elvisaurus and bladed-tailed ankylosaurs and ancient goblin sharks and 5-meter flying reptiles has done something to your sense of what this planet is and has been, then I would invite you to do two things. First, share this with someone who loves science, with someone who thinks they don't, with a curious child or a skeptical adult or anyone who has ever looked at the natural world and felt even a flicker of wonder. Stories like this one deserve to travel. And second, stay curious, because there are more stories like this one, more buried worlds, more extraordinary chapters in the history of this planet waiting to be told. And we will be here, every step of the way, to tell them. Until next time, this is David Attenborough. And all of this is our planet.